Okay, so good day. So in this video, we will solve several examples regarding biaxial and triaxial stresses. Okay, so first problem we will going to solve is this problem, 2.30. So this problem, so from easy. Okay, so a sheet of copper is stretched biaxially in the xy plane. So if the strains in the sheet are epsilon x, or the strain at x is equal to 0.40 times 10 to the negative 3, and strain at y is equal to 0.3 times 10 to the negative 3, determine the stress at x and stress at y. So use 100E, or the modulus of elasticity, equals to 110 gigapascals, and V, or the Poisson's ratio, is equal to 0.35. Okay, so this is our short solution to the problem. So this is our first answered problem in this video. Okay, so I just copied the question. So this is the solution. So you just use this formulas, okay. So by substitution, so we get these values. Okay, so first, be vigilant while solving. So please be vigilant while solving. So here, since the gigapascal is equivalent to 10 to the power of 3 Newton per mm squared, that one. So I convert it to Newton per mm squared by multiplying it by times 10 to the cube. And so I just copied the value of epsilon x and y respectively, and the Poisson's ratio, and put it in this equation. So I get the stress at x is 63.305, while the stress at y, okay, so I just put everything in this equation. So I just converted the E into Newton per mm squared by multiplying it by 10 to the cube, and then copying everything and put it in this equation. So I get 55.157 megapascal for the stress in y. So this is the answer. Stress in x is 63.305 megapascals, and stress at y is 55.157 megapascals. Okay, so that is the problem and the solution. Okay, so we proceed to the next problem. Okay, so our second problem for this video is this. So the rectangular block of material of length L and cross-sectional area A hits snugly between two rigid lubricated walls. So derive the expression for the change in the length of block due to the axial load P. Okay. So here we are going to derive the equation or the expression for this one. Okay, so we have this figure. So we see that there is an applied force. Okay. So we apply here at the top. And this is the cross-sectional area. Okay. I know this is the cross-sectional area, I mean. Okay, so this is for another problem. So this is the cross-sectional area, 2.32. Okay, so this is the solution for the problem. Okay, so here, so I just copied everything, and again we just use the equation for biaxial loading. So this is the equation. Okay, so here, since the epsilon y, or the strain at y, is equal to 0, so here, okay, it will become EY is equal to 0 because it could not move along y direction, only in x direction. Okay, so here we have x and y direction. So in y direction, since it is restrained, it fits snugly between the lubricated wall, so it should be 0. Okay, So it will be only in x direction will it can move. So therefore, the stress at x is equal to epsilon x e 1 minus v squared, since epsilon y, or the strain at y, should be 0. So here, since this P is compressing the rectangular block, so therefore it is negative. Okay, negative since it is in compression. So stress x is equal to negative P over the A. The A here is the area. Okay, so from that problem here, the area. Okay. So since is that, so negative P over A is equal to epsilon x times E over 1 minus V squared. Okay, so by algebraic manipulation, so it will become, if you multiplied 1 minus V squared both sides, so it will become negative P over A times 1 minus V squared over epsilon x over E. So therefore, we can compute the value of epsilon x is equal to negative P over EA multiplied by 1 minus B squared. So that, okay, so that is epsilon x. So we're not done yet. So since we get the value of epsilon x, so we put it in that equation. So therefore, okay, since the epsilon x is equal to elongation x over L, okay, so therefore elongation x over L is equal to negative P over EA times 1 minus B squared. Okay, so therefore our answer, okay, the expression for the change in length, okay, so therefore the change in length, or the elongation, is equal to PL over EA times B squared minus 1. Okay, so why? Okay, so this is already a good answer, but somehow there is a negative sign, so we can flip this one here inside the parenthesis. So we get the elongation at x is equal to PL over EA. So exactly what is the answer for this problem, or this is the expression for the change in length of the block due to the axial load P. Okay, so we will just review the solution for this. So this is the solution for the derivation of expression for the change in length of the block due to axial load P for problem 2.32. Okay, so this is the solution. Okay, so we get now to the next problem. So here we got, so we go to 2.36. Okay, so a torsion test shown. Okay, so okay, so here is the next problem. So there is no figure for this problem. So a torsion test shows that the shear modulus of an aluminum specimen is 4.60 times 10 to the 6th psi. So when the same specimen is used in tensile test, the modulus of elasticity is found to be 12.2 times 10 to the 6th psi. So find the Poisson's ratio for the specimen. Okay, so without further ado, so we will go to the solution. So this is our short solution. So I just copied the problem and then go directly to the solution. Okay, so for this problem, we just use this formula. Okay, so we have the value of E modulus, shear modulus. What is given is the shear modulus. So the shear modulus is G, and we find the modulus of elasticity. So if we find the Poisson's ratio, rather, so we have modulus of elasticity E and modulus of shear modulus G. So we just substitute. G is 4.60 times 10 to the 6 psi, and E is 12 times 10 to the 6 psi. Okay? So by algebraic manipulation, so we just, okay? Okay, so it became, we just multiply both sides by 2 times 1 plus b in order to eliminate this one. So it became like this. 2 times 4.60 times 10 to the 6 is 9.2 times 10 to the 6 times 1 plus v. Okay, so to make the long story short, we get the value of v, or the Poisson's ratio, as 0.326. So this is the, okay, so this is the problem, and this is the solution. Okay, so I hope you understand the solution of our example problems.